Hello YouTube viewers, this is Victor Echo 6 Whiskey Golf Mike here with you again. Welcome to my amateur radio hobby workbench. I've been working pretty hard here trying to build something that I can give myself a little bit more space to spread out on. And unfortunately, I think what's happened is I've given myself more space to have more clutter. So I had to have a little cleanup session here before I made this video for you guys. And yeah, hopefully it works out. So today's subject is dipole antennas, antenna feed point impedance with relation to the antenna height above ground, baluns, and of course using the nanoVNA to try to gather as much information about these things as possible so that we can make informed decisions with regards to antenna tuning and what type of RF transformer or balun we're going to use to feed the antenna. So before we get started, I wanted to show you guys something here. I got this strange parcel in the mail, and I really honestly had no idea what was going on or what it was. But there wasn't any markings on it really to suggest that it was amateur radio related, so I had no idea who this person was. But when I opened it, I found a letter inside, and it was signed by Kilo Charlie 3 Uniform Delta Zulu Mugs. So this was really something. I can't quite say I've ever experienced anything like this, but I'm assuming that what you've seen was me trying to keep my nanoVNA at an angle so it didn't reflect the light, and so I built one of these a little stand here out of cardboard, and it's really not very good, but it works. So perhaps Muggs took mercy on my predicament and had the skills and ability with a 3D printer to print me off a really nice stand here. It holds the VNA just at the right angle, and it's got a drawer here so you can store your calibration standards and your lead wires, and it's very sturdy. It's even got my call sign molded into the side of it, which is really cool. So anyways, this was a very exciting thing to see. So back to the subject of the video. You might notice that I've got a DG0SA design 1-to-1 current balun with some bare copper here. And what happened is I was operating one day. Typically I operate 80 meters regionally, and I'm not too interested in DX, but 20 meters was wide open that day, and I decided I wanted to try to make some contacts. So I went about tuning my 80 meter dipole to work on 20 meters, and I was able to get a match, but it was quite fussy. So after a little bit of success, I decided that I would try to bring up the power a bit. So I turned on the old AL80B and put some power to the antenna, and lo and behold, I noticed some strange behavior on the needles, and this is the result. I believe what's happened here is it is arced over and burnt the coating of the magnet wire, and I've actually removed the black magnet, the coating here, so you can see it a little bit better. But yeah, it's ruined my balun. So anyway, I wanted to take this opportunity, now that I've pulled the dipole down and taken my balun apart, to share with you the thought process that I went through when I was building my station here for NVIS operation, which requires the use of a fairly low mounted antenna. And I have enough room. I'm lucky to have the room to put up a full length dipole for 80 meters, which I've done. It's a pretty lazy or quite open inverted V configuration with the feed point at about 35 feet off the ground and the end sloping down to about 6 to 8 feet off the ground. So in the research that I did when I was building my station here, I ran across some information, and this chart I just pulled here today and printed off. This came from the Cascades Amateur Radio Society webpage, and it shows the general behavior or the generally expected behavior of a dipole as you lower the feed point down towards ground closer and closer. So my antenna being at around 30 feet height, I'm sitting somewhere in this range here, I believe. So I assumed, based on that I'm probably sitting around 25 ohms in input impedance, feed point impedance. So here's the question. Everybody uses a 1-to-1 current balun, but what about matching 50 ohms down to the 25 ohms? So what I did was I went in and did some research, and this is one of Sevic's designs, and this is a 2-to-1 un. So what this does is it takes 50 ohms in and it produces 25 ohms out. So what I did was I connect the coax cable to this right here, and then this comes through and transforms it from 50 down to 25, and then that is then run through the balun transformer so that it converts the 50 ohm unbalanced to 25 ohms balanced to feed my dipole. So this is all based on a guess, though. I didn't actually take the time to measure, and I think when I did that, I didn't have the skills with the nanoVNA to even attempt it. So we're going to go do this process again, and I'm going to try to step it up a notch, and I'm going to try to analyze what I have here, and we'll see if my choices are correct. So the first problem with this project is, how do we take and connect our nanoVNA to the antenna that's mounted at 35 feet in the air and make measurements? Typically we use a short piece of coax cable, 8 inches, and we use our cal standards here to calibrate the nanoVNA so that we can make measurements at this point, which is then becomes our calibration plane. So if you look at the picture here, and I've drawn this I think for you guys in the past, here's our nanoVNA, our transmission line, our device under test, and this is our reference plane that we have calibrated at, so that the nanoVNA will then take anything after this plane and examine it. So what we're going to do is I'm going to take the nanoVNA, I'm going to connect this to my RG213 coax cable that runs down into my radio room, and it's 100 feet long, and it goes out up to my dipole antenna 36 or 35 feet above my roof of my house outside. So what I'm going to do is I'm going to, instead of using this short piece of coax, I'm going to use that 100-foot piece of RG213, and I'm going to calibrate at the end of the RG213, just like it shows here. The transmission line, instead of being 8 inches, it's going to be 100 feet. And our new reference plane will be out at the end of that cable, right where it connects to my dipole antenna. We're going to use the calibration standards at that point to set up the nanoVNA. Okay, so seeing as how Muggs has gone to all the trouble to 3D print this really nice nanoVNA stand for me, I'm going to use the H4. This stand is actually printed specifically for the nanoVNA H4. I do prefer my nanoVNA F because I think it has a nicer display, but today we're going to use the H. So the first thing I've done, I've already gone and done that, we probably don't need to go through it again, is to calibrate the nanoVNA. I've selected the start frequency and the stop frequency, 10 kilohertz to 30 megahertz, and I've brought up the variables that I want to look at, the readouts, SWR, the Smith value, so I can see the real and reactive components in capacitive or inductive notation, and I want to see the log mag so that we can make the loss measurement of the coax cable. I want to double check my coax while we're doing this, and the polar display, which gives me the readout in complex notation. So here's the thing. I've told you earlier that we were going to calibrate the nanoVNA at the end of the RG213 coax, which we are going to do. But here's the reason, there's two reasons actually why I've calibrated at the end of this short stub of wire here. First off, we can use this to test the nanoVNA to make sure we have a solid test apparatus. You can see that I'm bending this around. These cables sometimes do go bad, or there's bad connections that happen. If you notice the readout, it didn't move at all. So we have a good solid piece of coax, the connections are good, and everything looks happy there. The second reason why I've calibrated at this point right here is so that we can make these log mag measurements on the coax cable before we get started, so that I can verify that my RG213 coax is actually still good. So we're going to go ahead and hook the nanoVNA up to the RG213, and then we're going to start the return loss method of calculating the loss in this cable. And then we're going to compare that to what a new piece of RG213 would be for the same length at the same frequency. Okay, so I've gone ahead and hooked up the cable, the nanoVNA, to my RG213 using PL259 to SMA adapter that I had in my kit. And I'm going to make a change here on the nanoVNA. I'm going to take the stimulus and make it a CW frequency of 10 megahertz. So it's only producing one frequency, and we're going to take our log mag readings at that one frequency so that we can compare the loss that we're going to calculate in this cable to what is published specifications for RG213 at 10 megahertz. Okay, so the reason why I've got the my camera off at a weird angle is because this VNA has a fairly reflective screen, and it's pretty difficult to find an angle that doesn't reflect light or act as a mirror, and you'll be seeing my face in the screen of the nanoVNA, which is pretty distracting. So we've hooked up here, and we've got our first reading at 10 megahertz, and you can see negative 1.66 dB. So we're going to go, we actually did this in a previous video. The total loss of the cable is equal to the return loss with the cable shorted plus the return loss of the cable open divided by 4. So this is the formula for calculating that. So I've taken this first reading, 1.66, and I see I wrote 1.64 down here. So we're going to change that to 1.66. And then we're going to run outside, and we're going to short the cable using the Cal standard. That's this one right here for the short. And I will be right back to make another measurement. Okay, so I've come outside to the end of the 100-foot length of RG213, and I've hooked up the short on the end of the cable, and now we're going to run back inside and see what the nanoVNA has to say. Okay, so we can see that the nanoVNA is showing about 1.8 dB with the end of the coax shorted. So I've gone ahead and added that into the formula here and done the math on the calculator, and I come up with a result of 0.865 dB of loss using the return or the cable loss measurement or the return loss measurement method. I've looked up the specs on QSLnet, the coax cable loss calculator for RG213, and at 10 megahertz, 100 feet, we would be expecting 0.622 dB of loss. So we're seeing a little bit of extra loss. Now I'm not sure if that's coming from my cheap connectors or if I'm actually seeing a problem in the cable itself starting to degrade. I tend to probably lean towards the fact that I'm using cheap connectors and we're losing a little bit there. It is only 0.2 of a decibel difference. So I'm not going to worry about my RG213 coax at this point. If I was worried, what I would do is I would probably take and put some power to the coax and put a dummy load on the end of the coax with a RF power meter. And of course the dummy load would need to be rated to handle the power. I would probably put 100 watts through the cable and then see how much loss I get based on the input and the output, and then make my determination from there. But at this point, this is not triggering me really to investigate any further at this point. One thing I just thought of that I should probably make note of is once these measurements, this kind of a measurement has been taken at your station, especially for a semi-permanent or a permanent installation, make note of the value obtained and the measurement method that was used to obtain that value and the date. So what this is going to do is in the future, if you make these measurements again, you're going to notice if there's any degradation in the coax or change there. And I think that's actually more important to watch the change over time rather than just simply comparing, one value to what we think it should be based on a online calculator or the manufacturer's specifications. There's going to be slight differences because of the losses in the connections and couplers and things like that. So I think that if you install a new station, probably a good idea to make those measurements when everything is new, and then you can watch if there's any change over time, and that's going to give you a very good indication that something is changing and that you might need to look into things. All right, so I've got my 3 cal standards here with me, and of course we know that the nanoVNA is going to be asking for the open first, so I'm going to go ahead and connect the open, and we're going to run back in and reset the nanoVNA's calibration. Okay, we're back inside now. The open standard is connected out at the end of the 100-foot coax, and before I get crazy with resetting the calibration and starting over again, I have to remember to set the stimulus back again to 10 kilohertz to start, and then I'm going to stop at 30 megahertz. And now we've got our calibration, the range of frequencies that we're going to calibrate through. Sometimes I'll go and recalibrate and forget to set the span, and then I have to go do it again, which is kind of a pain. So we're now going to go into the calibration menu, then we're going to reset the calibration and start our procedure using the open. Now we're going to connect the short and the load, and I'll be back when all of those are completed. So I've completed the open, short, and load calibration with the nanoVNA, thereby moving that reference plane out to the end of the 100-foot coax. And you can see that I've left the 50 ohm cal standard connected at the end of the coax, and it's showing exactly where it should, right dead center at 50 ohms, non-reactive on the Smith chart. I'm going to take my power 50 ohm dummy load out there and connect it. And in theory, we should see this marker show up in exactly the same place. So let's do this little experiment and see what happens. All right, we now have the dummy load connected instead of the cal standard. So let's go back inside and see what the nanoVNA is showing. And what do you know? We see the marker is right dead center, showing that we have a 50 ohm load connected to the end of the coax cable. And just out of curiosity, I looked at the log mag, so this is our return loss. It's fairly flat across the frequency spectrum, which is what I would expect given the fact that we don't have any kind of reactance on the end of that coax cable to interfere with the frequency response of this curve. It should be a fairly flat line. The SWR is showing 1:1, so we have a perfect match out at the end of that coax cable, which is what we should expect given the fact that we have a 50 ohm resistive load connected. Perfect. One of the really great things that the nanoVNA has done for the amateur radio hobby is it's allowed the average operator to ask questions and to have an opportunity to experiment and answer those questions in a manner that was previously not available to us. So my question today for this video is that I'd like to experiment and see is what is the difference if I hook an unbalanced feed line direct up to a balanced dipole antenna? What's the difference between that and if I hook it up through this balun transformer? Is there going to be really any change in the behavior that the nanoVNA sees? We're going to try and answer that question, and I have no idea what the outcome is going to be, and it'll be interesting to see. We're out here at my 35-foot mast, and we've got the dipole fixture built and in place, and we're going to send it up and away. Well, I've taken and removed all of the traces except for the SWR graph, and we're definitely seeing something here. I'm gonna guess that this one down here is the fundamental resonant frequency of the antenna, and let's go down and see if we can figure out. Yeah, it's down around 3.9. So I'm gonna take and change the stimulus to let's go with 3 megahertz, and let's stop at 4 megahertz. And we'll hone in on where that lowest SWR. So it looks like the antenna is tuned right now for 3.810. So now the resonant frequency of the antenna, how do we know it's at resonance? Resonance is not necessarily the lowest SW, the point where the SWR reads lowest. Resonance, the fundamental definition of resonance is the point at which the capacitive reactance and the inductive reactance of the device cancel out. They are equal and opposite, and all that's left is a purely resistive load. So let's go back in and use the nanoVNA to see where that point is. Using what we know about the point of resonance being neither inductive or capacitive, it's non-reactive and presents simply a resistive load. Let's see if we can use that to determine where this antenna is resonant. So I'm looking right now at the Smith. You can see it's reading capacitive right at the moment. So it's below the center line. If it was above the center line, this would be reading inductive. So let's go ahead and change the frequency here that we're looking at. And we're going the wrong way, you can see. So I'm just going to make a note of this. 3.850 megahertz is 2.9 nanofarads. So at 3.85, we're capacitive. I'm going to actually write that down. And we're going to go too far the other way. At 3.75 megahertz, we are inductive. We're going to come back to this point of resonance at 3.81. Now, how do I know it's resonant? Well, this one is bouncing around a bit. Let's use the polar here. So if this value is 0, this is the reactive component. If this value is 0, then there's no reactance. That means it's not capacitive, it's not inductive. So let's adjust this until this reads 0, and then you can read the frequency. 3.809 megahertz is exactly the point of resonance on this antenna. Does that mean that the SWR is 1-to-1? Well, no, because you can see where the point, the 50 ohm point, if it was a perfect match, it would be right here dead center on the Smith chart, which is 50 ohms, but it's not. It's actually shifted towards the higher impedance side, and you can read that here at 65.5 ohms. So this is another interesting result, actually. According to this chart that I was looking at and the assumptions I made when I originally built this antenna, if I've got an antenna mounted at 35 feet height, that's 10.67 meters, which is just a little over 0.1 wavelength at 80 meters. 0.13, I think, is where it, yeah, 0.13. So I was expecting the impedance of the antenna to be reading around 25 ohms. The fact that we're getting 65 ohms is somewhere up here. According to this chart, it would be at about, I would expect to see that at about 0.2 wavelengths above ground, which is 16 meters. So I would expect to see that at 65 feet, or at 52 feet, 65 ohms at 52 feet. So that's a very interesting result, and this is one of the reasons why I've absolutely fallen in love with the nanoVNA, because we can perform these kinds of experiments and come up with results that are very interesting. So earlier I said we were going to make note of some frequencies, and I just wanted to point out some behaviors. In the case of my antenna here, at 3.81 megahertz, we found that that was the point of resonance, and that's where the antenna reads purely resistive. Now here's something interesting. Okay, so this was about a year ago that I originally filmed this video, and I apparently made a mistake. My point of reference was incorrect. Everybody knows that an inductive antenna means the antenna is too long, and a capacitive antenna means that it's too short. Somehow I managed to get this backwards. So I've gone ahead and done another experiment here, and I've taken a short piece of wire because this is much easier to deal with than a full-length 80-meter dipole outside at 35 feet in the air. So I've taken and calibrated the nanoVNA at this reference plane right here and measured it, and it's resonant at about, let's see here, looks like about 173 megahertz. Let's take a look at this. The reactance is currently jumping around. Now it's steady. Okay, so about 34, 60, I don't know, it's in the milliohms region, so it's very, very close to resonance, which is this point here where it's neither inductive or capacitive. So you can see here we're reading, it's jumping between inductive or capacitive because it's really close. So I'm going to go ahead and trim this antenna now, and it's going to probably shift the frequency of resonance up. Well, it will. We know it will. So I'm going to trim about an inch off of here. And we'll go back and look. And you can see that the frequency of resonance, this point where it crosses that central line, has shifted up. That's quite difficult to see. Let's get rid of some of these. Oops, display. The Smith, that simplifies it. All right. There we go. So this makes it quite a bit easier to see. So you can see that that point of reference, or that the frequency of resonance has shifted up, and where it was at 173, it's now up. So what's happened here? We are now negative 10 ohms reactive, and if we go back and look, that means we're capacitive. Look at the Smith value. It's capacitive. So that means that a short antenna is going to read capacitive, and a long antenna will read inductive, as expected. So I'm going to have to go ahead and correct these notes here. And yeah, my eraser wasn't working very good, but a long antenna is going to read inductive, and a short antenna is going to read capacitive. So I wanted to make that clarification and repost this video and make sure I'm not leading anybody astray. Back to the subject of the feed point impedance of the antenna. This was a very interesting result. At 65.5 ohms, I was expecting something more along the lines of around 25 ohms, especially given the information that I had and the charts. And I'm going to guess that because of the distance, the actual ground, that reference point that the antenna uses to reflect off of is different at my location. It could be something to do with soil conductivity. It could be something to do with the fact that I have recently put some tin roofing on my garage. I'm not exactly certain, but this was definitely not the expected result. So one of the things I was curious to know, or curious to experiment with, and I'm going to do this next, is to see exactly what effect lowering the antenna has on that feed point impedance. Now, according to the graphs that I've seen, it looks like the lower I go, the lower the feed point impedance. So we're going to try this experiment and see if that's how it behaves at my location. So I've gone and lowered my antenna, the center feed point, down about a third of the way down the mast. And I've readjusted the nanoVNA here to look for that point at which the reactive component is 0, and that happens to be at 3.791 megahertz. So that's interesting. My feed point impedance is now 67 ohms. So with it higher up, it was at 65.5 ohms, lowered down 67 ohms. With it higher up, the frequency of resonance of the antenna was 3.809 megahertz, and with it lowered, it's dropped now to 3.791 megahertz. So that's very interesting results. So I actually don't have any explanation as to why this is behaving exactly opposite of what we would expect based on this chart. But as in a lot of cases in the real world, what is modeled or theoretical, there's so many factors at play that it's pretty hard to take into account everything that could possibly be going on here, at least for the average person such as myself. So again, the nanoVNA is telling me what is actually happening, so I'm not guessing based on theory, and the theory is not taking into account all of the factors at my location. So you're probably best to actually take those measurements at your location and find out the behavior of your system at your location, because what you would expect might not be true. All right, everybody, so there was another question I wanted to ask and investigate with the nanoVNA, and that was, what is the difference between connecting a balanced antenna directly to an unbalanced feed line as opposed to connecting a balanced antenna through a balun transformer to an unbalanced feed line. I wanted to know what the nanoVNA would see, if there was any difference between the two, or if it would change the behavior of the antenna at all. Anyhow, I've got about 30 minutes worth of video here, and I think that's probably enough for today. So I'm going to take and maybe revisit this subject and perform those experiments again in another future video. So for now, I guess one last time, I'd like to send a great big thank you to Muggs, Kilo Charlie 3 Uniform Delta Zulu, for taking the time to construct this really fantastic nanoVNA stand and spending the money to send it, you know, in the mail. It's a significant gesture, and I think that the whole spirit of amateur radio, that's what it's all about, is you know, just being decent with each other, experimenting with things, learning, sharing, and you know, this is just excellent. So Muggs, I hope one day that we can get on the air and have a QSO, and I'll be trying to get a hold of you here in the future, and I'm gonna wrap it up here now and call it a day. It's getting dark outside, so I don't want to really be climbing up on the roof, performing more experiments and wind up falling off and breaking a leg. So this is where we're gonna shut her down here for tonight. Okay, thank you very much for watching, everybody, and I hope to see you again next time. This is Victor Echo 6 Whiskey Golf Mike.